Good morning. Today we'll begin our study of linear algebra. So what is linear algebra? The fundamental theme is solving systems of linear equations. But linear algebra is a branch of mathematics full of theory and applications. It can involve many arithmetic steps, so it is absolutely essential to avoid making careless errors. This branch of mathematics arose from the study of systems of linear equations. It's not unusual to have hundreds or thousands of variables in these equations, those that represent real-world situations. Of course, the ones that we'll be working with will be limited to 3, 4, or 5 variables just to learn the process. If you can learn the process with a few amount of variables, then you can certainly apply that to a situation where you have more variables. So it's important that we learn to develop an algorithm that will help us solve large systems of equations in some ordinary manner. In Algebra 1 and also in Algebra 2, you should have studied solving systems of linear equations. But we're going to develop an algorithm that will help us solve systems that involve many variables. A linear equation in n variables could take the form of this first equation here. The a sub 1, a sub 2, a sub 3, etc. are coefficients. B is a constant term, and it is a real number. And then x sub 1, x sub 2, x sub 3, etc. are the variables. Linear equations have no products or roots, no trig functions, no exponential functions, or logarithmic functions. So let's take a look at some examples of linear equations, and then we'll also take a look at some that are not linear equations. So a linear equation in 2 variables might be 3x plus 2y equals 7. Another example, 1/2 x plus y minus pi times z is equal to square root of 2. So this linear equation has 3 variables, x, y, and z. The coefficients are real numbers, and we have a constant, square root of 2. Another example, sine of pi over 2 times x sub 1 minus 4 times x sub 2 is equal to e squared. Well, now wait a minute. I just said no trig functions, no exponential functions. Okay, I didn't lie. This is a number. The sine of pi over 2 we know to be 1. E squared is also a number. It is not a function. E squared is our irrational number e, approximately 2.718 raised to the 2nd power. So all 3 of these do represent linear equations. Some examples that are not linear, just so you can be clear to understand the difference. X times y plus z is equal to 2. We have a product that makes it not linear. Sine of x sub 1 plus 2 times x sub 2 minus 3 times x sub 3 equals 0. Okay, here we have a trig function. We're finding sine of the variable x sub 1. That is not a number. I mean, it varies depending on what x sub 1 is. And one more example. 1 divided by x plus 1 divided by y is equal to 4. This does not represent a linear function. Next, we'll look at a parametric representation of a solution set. To solve the linear equation x sub 1 plus 2x sub 2 is equal to 4, we could first begin by saying that x sub 1 is equal to 4 minus 2 times x sub 2. So x sub 2 then is the independent variable. Suppose we let x sub 2 be equal to t. That would mean then that x sub 1 is equal to 4 minus 2 times t. So we've represented our linear equation as a set of parametric equations. Two equations, both having the independent variable t. Both of these equations depend on what t is. So if we wanted to suppose that t is 1, then that would mean our solution x sub 2 would be 1 and x sub 1 would be 4 minus 2 times 1, or simply 4 minus 2, or 2. Let's take another example. This linear equation has 3 unknowns. So if we begin by solving for x, we could first get x by itself by subtracting 2y and adding z to both sides. So that would give me negative 2y plus z plus 3 on the right-hand side of the equation. And then to finish up getting x by itself, I need to divide everything by 3. So x would equal negative 2/3 y plus z divided by 3, or 1/3 z, plus 3 divided by 3, or 1. So in this case, we have two variables that x depends on. So rule of thumb, we start with the last variable, the z, and we name it t. Then we take the next variable, which would be y, and we call it s. So renaming x and y using s and t, we then can say that x is equal to negative 2/3 times s plus 1/3 times t plus 1. Then to get a solution, we could choose numbers for t and s. Suppose we let t equal 0 and also let s equal 0. Then that would mean x is 1 because negative 2/3 times 0 is 0 and 1/3 times 0 is 0, so that only leaves you with 1. And then of course y would be 0 if s is 0, and z would be 0 because we let t equal 0. If on the other hand we started out by saying let t equal 1 and s equals 2, then x would be negative 2/3 times 2 plus 1/3 times 1 plus 1, which is negative 4/3 plus 1/3 plus 1, which is 0. So we would have x is 0, y is since y is s, y would be 2, and z being t, z would be 1. So we solve the equation for x, and then by choosing whatever we wish for s and t, we can get a solution to that parametric equation. Let's bring our focus back to systems of linear equations. A consistent system has at least one solution. It may have exactly one solution, or it may have an infinite number of solutions. An inconsistent system, on the other hand, has no solution. So what we're going to do is use a graphing utility to graph the equations in a given system. We can then use the graph to determine whether the system is consistent or inconsistent. If it is consistent, we will approximate the solution, and then we will solve algebraically. Let me give one word about calculators in this course. They are only to be used when directed. And believe me, it will be tempting to grab that calculator going through these tedious arithmetic calculations. Don't do it. You need to do the problems without the calculator unless it's a calculator active problem. So the purpose of this exercise is to understand the difference between consistent and inconsistent graphically, and then we will solve the systems algebraically. So beginning with this first system, x plus y equals 3, and x minus y equals negative 1. Well, if we want to use a graphing utility to graph this system, we need to solve the equations, both of them, for y, because we have a y equals screen. So when we solve the first equation for y, we have y equals 3 minus x, or you could also say negative x plus 3. In the second equation, solving for y, if I add y to the right-hand side, at the same time add 1 to the both sides, moving it over to the left-hand side, I get the equation y is equal to x plus 1. So there is my system of equations I want to analyze graphically to determine whether it is consistent or inconsistent. So from my graphing calculator, I'm going to go to the y equals screen and type in the first equation, negative x plus 3, and the second equation, x plus 1. And I'm going to look at this in the standard viewing window, so I will zoom 6. And what I see is that the two lines do intersect. That point of intersection is the solution to the system. Just trying to read the grid, it looks like the solution is 1, 2. There is a way to use the calculator to find that solution, to let the calculator find it for you. But we're just approximating here, and then we're going to solve algebraically. So I'm thinking the solution is somewhere in the neighborhood of 1, 2. Now to solve algebraically, what I could do is add these two equations together, and that gives me y plus y is 2y, negative x plus x is 0, and 3 plus 1 is 4, so that y is 2. And once I find the answer for y, I can plug it back into either one of the original equations and solve for x. Incidentally, working back from the original equations before I had solved them for y, let's just take a look at that. Again, if you add the equations together, you have x plus x is 2x. The y's are eliminated. 3 plus negative 1 is 2, so x is 1. And then I found x first in this case. If I put my answer for x back in place of the x in either one of the original equations, I can solve for y and find that yes, y is 2. So the solution I approximated from the graph, 1, 2, is in fact correct. This system has a solution. That means it is a consistent system. And the fact that the system only has one solution makes it an independent system as well. So we would categorize it as consistent, independent. Okay, let's work this next one together, and then I'll let you do the third one by yourself. So I need to get these equations ready to type into my y equals screen. That would be y equals negative x plus 3. And subtracting 2x and then dividing all terms by 2 gives me y equals negative x plus 3. Well, that's interesting. The two equations are the same. Perhaps you recall what this means from Algebra 1 or 2, but let's see. So I want to enter these two equations into my y equals screen. And you know, the fact that I'm entering the same equation should not surprise me that I get the same line for each. And if you were able to watch that quickly, the equation 1 was graphed first in blue, and then equation 2 graphed over it in red. So let me make a change here so you can see that again. There's the blue, there's the red. You have to be fast. So this is also a consistent system. But since we have an infinite number of solutions, we refer to it as a dependent system. The solution, when we're looking at the graph, there wasn't just one point where they intersected. The two lines intersected at every point on the line. So in other words, the solution would be all points on the line and since there are an infinite number of points on a line, there are an infinite number of solutions. And so that makes it consistent because we do have solutions, but it is dependent. The way I remember it is that one line depends on the other. It's right on top of it. They coincide. So how would we solve this one algebraically? Of course, if I add the equations together, nothing would be eliminated. So what I would need to do is multiply a row by an integer so that the coefficients of one variable is opposite. When I say multiply, remember that division is the inverse of multiplication. So what I'm going to do is I'm going to take my first equation and leave it just like it is. But my second equation, I'm going to divide it by -2. Multiply by -1/2, divide by -2. Okay? That gives me a brand new equation, -x minus y is equal to -3. Well, now I can add the equations together and notice that both the x and the y are eliminated. And I end up with a statement that is true. Since that statement is true, that confirms that the system is consistent dependent. There is an infinite number of solutions, which would be all points on the line. Okay, I'd like you to pause the video and solve the third system here. Again, get each equation ready to graph them in your calculator, approximate the solution, then go back and solve it algebraically and state the solution. Also state whether it is consistent or inconsistent along with your solution. So you've entered the equations y equals negative x plus 3 and y equals negative x plus 1, and you find that those two lines do not intersect. In fact, the lines are parallel. They are parallel because they have the same slope. This system has no solution. There's no point that the two lines have in common. So in the event that there is no solution, the system is called inconsistent. And solving it algebraically, when you eliminate x, for example, you get a bonus, and y is eliminated at the same time, but you're left with a false statement, and that backs up the fact that the system is inconsistent and there is no solution. Moving on to another topic, solving a system that is given in row echelon form. So first of all, row echelon form. You notice here that there are 3 variables involved. The number of variables determines the number of equations that you must have in order to solve the system. And in this equation, in the system, it is said to be in row echelon form because the variable z has a coefficient of 1 and it's in an equation by itself. Then you have an equation involving y and z, where this time the y has a coefficient of 1. And then your third equation has all 3 variables with the x having a coefficient of 1. So to be in row echelon form, you have a coefficient of 1 on the leading variable in that equation. We can solve this one very easily using what is called back substitution. If we know that z is 2, we can quickly find y by taking the second equation and replacing z with 2. So y plus 3z equals 5 becomes y plus 3 times 2 equals 5. Solving for y, I have y plus 6 is equal to 5, so that means that y is negative 1. Well, if I know z and y, I can then find x using the first equation. I have x minus 2 times what I found for y plus 3 times what I have for z. So I have x plus 2 plus 6 is equal to 9, or x plus 8 is equal to 9, so then x is equal to 1. So the solution to my system is x equals 1, y equals negative 1, and z is equal to 2. Moving on then to Gaussian elimination. We want to use Gaussian elimination to rewrite a system in row echelon form. So again, what we want to end up with is 3 equations so that the first one involves all 3 variables, the second one involves 2 of the variables, and the third one only 1 variable. And in each case, the coefficient of the leading variable is 1. Now, when given a system, you're allowed to rearrange the equations if you want to, if it's helpful, to help you achieve that goal. So studying this example, I see, wow, whoa, what if that one were written first? Well, let's do it. So I'm just going to rearrange my equations, putting that one first, and then the first one second, and then the third one last. You can rearrange as needed to get the coefficient of 1 on that first variable, but you can only do that the one time. So you do it before you start the process. Now, what I want is for this coefficient to be 0 and for this coefficient to be 0. I need to end up with a 1x on the first row, no x's on the second row, and no x's on the third row. In other words, I want a 1, 0, 0. So we begin the process of Gaussian elimination. I take my first row and write it down. And what I want to do then is multiply that row by the opposite of the number I'm trying to change to a 0. So if I multiply this row by -2, that's the opposite of +2. So let's do that. -2 by each number. That gives me -2x plus 4y minus 6z is equal to -18. After doing that, I want to copy down the row I'm trying to change and then I will add those 2 equations together, thus eliminating the x. And that gives me my new second row. In this iteration, I also want to change the coefficient of this x to a 0. I see now that the coefficient is -1. So, with that being the case, I take my row 1 that has the 1 in place where I want it. I multiply that row by the opposite of the coefficient I'm trying to change. Since I'm trying to change this -1 to a +1, I would multiply this row by +1. Well, what's that going to do? it's not going to do a thing. It will not change that row at all. I then copy down the row that I'm trying to change under it, and now I'm ready to add those two together. So I have y plus 3z is equal to 5. That becomes my new third row. So my first iteration is complete. I have transformed my system so that my first column here has a 1x, a 0x, and a 0x. You don't need to write the zeros. I'm just putting those there for a second to make you understand the process, or help you to understand the process. Okay, well, my next step, I want a positive 1 right here on the y, and under it I want a 0y. So my first row is good. I'm going to rewrite that row. And now to change my second row so that this coefficient of y is a positive 1, I need to divide it by negative 1. I divide that entire row by negative 1, which will give me positive y plus z equals 1. So now that row is good. I then need to use that row to change the coefficient of the y in the third row. I want the coefficient here to be 0. So what I need to do, the coefficient is 1. I need to take the row, my new second row, and multiply it by the opposite of the number I'm trying to change. So that means multiply it by negative 1. When I multiply my new second row by negative 1, I have negative y minus z equals negative 1. I copy the row I'm trying to change directly under it, and then I'm ready to add those two together to get my new row 3. So that gives me 2z is equal to 4. 2z is equal to 4. So that's the second iteration. We have one more iteration to go to get this in row echelon form. I want this coefficient to be a 1. I've got the 1 on the x, I've got the 1 on the y, so my first and second rows are complete. I have x minus 2y plus 3z is equal to 9, y plus z is equal to 1, and now I need to divide by 2 to make this 2 a 1. So 2z divided by 2 is 1z, and 4 divided by 2 is 2. We have now transformed the original system into row echelon form, and it can easily be solved using back substitution. In fact, you might notice that is the system we solved in the previous example. So starting with the system, you transform it to row echelon form, which means you want coefficients of 1, 0, 0. Whatever 1, 0. And then you want 1, 0, 0, whatever 1, 0, whatever 1. That gives you a coefficient of 1 on your first variable, 1 on the second variable, and 1 on the third variable, which makes it easy to solve using back substitution. Okay, let's look at one more example. To solve the system of equations, we're going to rewrite it into row echelon form and then use back substitution to solve. I'd like to get you started with this one, and then I'll let you pause the video and finish it. So you look at this, well, wow, it's really strange. It looks much different than the previous examples. Yes, it does, mainly because of this first equation. First of all, it is linear. It meets all of the qualifications to be a linear system, but we have these fractions. What we'll do is, first of all, multiply by something the denominators both go into so that we don't have fractions. In other words, find the least common denominator of 2 and 3 and multiply the equation by that. Since that would be 6, if I multiply my equation, both sides, by 6, I will have an equation without those silly fractions. 6 times the quantity x minus 1 over 2 becomes 3 times the quantity x minus 1. 6 times the quantity y plus 2 over 3 becomes 2 times the quantity y plus 2. And 6 times 4 is 24. Simplifying it further, distribute the 3, distribute the 2, combine the constants on the left, and then isolate the constant over on to the right-hand side, so that we have 3x plus 2y equals 23. That is the first equation transformed. So I have the second equation and the new first equation. So thinking ahead, since I would like to have a coefficient of 1 on the x in the first equation, I think I will write this equation first and then put my new transformed equation under it. So at this point, pause the video and transform this system into row echelon form. Yes, I know it can be solved quickly using elimination, but I'm telling you, if you understand how to work with a simple equation, transforming it into row echelon form, it's going to make it much easier to work with an equation, a system that has many, many variables in it. So transform to row echelon form and then solve using back substitution. Resume the video once you have finished. So my first step was to change the coefficient of the x in the second row to a 0. Since it was 3, I multiplied my top row by -3. I added my second row to it, getting my new second row. Iteration number 2, I want to change the 8 to a 1. So I divide by 8. That changes the 8y to a 1y. And now I have transformed to echelon form. I can then use back substitution to find that x is 3 when y is 1. More yet to come, but let's start in baby steps here. Again, learn the algorithm because it gets very tedious when more variables are involved. Don't assume that you can get by without learning the algorithm.